Alrighty, let's go ahead and get started. So this week, what we have going on, today we're going to work some example problems for Archimedes Principle, which we discussed last time. And I'm pretty sure we'll be able to finish it up today. And so I think the plan will be Wednesday, we'll have our exam review. So again, every exam I give in this class, I want it to be on one big overarching topic. And so since fluids is finished with Archimedes Principle, we're done all the theory, all we're doing is working examples now. This exam 2 will be just on the fluid stuff we've done. So Wednesday we'll do our final, or not our final exam review, just our exam 2 test review. We'll go over the topics, of course, give you a chance to ask me more questions, ask me to do some more examples if you need it. And then Friday, we'll have our second test. And again, that test will be posted online, just like the first test. So you're already used to the format, you're used to how all of that works. And so that's what we have going on for this week. Now, as it pertains to Archimedes Principle, let's review what Archimedes Principle entailed, because it's kind of a little awkward in that it's not one equation or one concept, but rather it's like a set of different relationships. And when you're given a problem that deals with Archimedes Principle, then it's up to you to choose which relationships may or may not be important. I see a question. Yes. What's up?
So the test is going to be on Bernoulli's and Archimedes Principle and continuity. It's going to be on all of those.
Yeah, so it's going to be this first topic, which is like the water flowing through pipes. That's Bernoulli's principle. And continuity goes with Bernoulli's principle. And then we had kind of the pressure depth relationship. How much pressure do you feel depending on how deep you go? And then Archimedes principle, which is going to be these relationships we're going to discuss some more today. So it's like 3 mini topics that are a part of fluids. Yeah, that's what you can expect. So Archimedes Principle, like I said, it had several different things put onto it. First, we have the fact that when an object is placed in a fluid, and let's say it sinks or it's under the water, then if you were to measure the weight of that object, it would weigh less than it would when it's not in the fluid. So you standing on Earth, if you stand on a weight scale, it's whatever your weight is. But if you're in the water and you stand on a weight scale, well, the scale will think you only weigh 20 pounds or something. And so the equation we could use for this type of thing is to say that the apparent weight of an object that's in a fluid is the true weight of the object minus the buoyant force acting on the object. And so the more buoyant force is there, the more the water is trying to push up and make you float, the lighter you're going to feel, obviously. And so that's the first relationship. The fact that when you're in the water, you feel lighter. What exactly is the equation that relates this? Well, if you happen to know the buoyant force, then you could figure out how heavy something would weigh in the water, or vice versa. You could say, well, it weighs 20 pounds when it's in the water. So how much should its weight actually be when it's not in the water? Let's say you're a diver and you're trying to gather things from the ocean floor, sunken treasure or whatnot. Well, that may be an important thing. You may be able to lift it up to the surface, but once it's at the surface, you then have to lift it up out of the water. And so it's going to weigh differently there. But then we had some other relationships. And these relationships all went together with each other. And this has to do with when an object is placed in water and we want to know something about the object. The first thing we know is that when an object is placed in water or any fluid, but we'll use water just as a stand-in, well, the water level will rise. And I'm sure we've all seen it, whether it's in a bathtub, you get in a bathtub, the water level rises, or you have a glass, you fill it with water, and then you put ice in it, and now the water overflows because you didn't have enough room for the ice. Well, this equation relates that, and what it says is that the volume displaced by an object, so that is how much the water level changes, is another way of saying it. The volume of the water displaced is the same as the volume of the object that was placed in the water. So if you put an ice cube in a glass of water, then there's an amount of water, which is the size of an ice cube, that had to get moved out of the way. And that's all this equation says. It's just a mathematical statement of the concept. And the concept is fairly intuitive. You want to put something in water, you have to move the water out of the way to let the object be there. And so the water level rises a certain amount because you move the water. Then it went further with one of the most important ones, which allows you to figure out something about the buoyant force. And what it says is, if you now take the water that was displaced, however you do it, maybe you just calculate how much water was there based on what the volume was, or you literally let it overflow over the surface and you gather the water. However you do it, if you weigh the water that's displaced, so the weight of the fluid displaced when you put an object in the fluid is the same as the buoyant force which acts on the object. And so this is one way of being able to, for instance, use the first equation. In order to figure out what the apparent weight of an object would be, if you know its actual weight, you need to know the buoyant force. But how in the world do you figure out the buoyant force that's going to act on an object? Well, the main way is using this principle. When you put the object in the water level will rise. You figure out what that volume of water that rose, how much water was displaced. And then you could calculate the weight of that. Now, how do you calculate the weight of the water displaced, you may ask? Yeah, I know how much water, but how do I get the weight from how much water? Well, that's what the last relationship says. It says, remember what weight is. I'll put it over here on the side just to remind us. Weight is mass times gravity, right? Well, in fluids, remember, we don't talk about mass. Mass is not as useful as something else, which is called density. And so I know mass, I'm sorry, not mass. I know density, rho, is mass over volume. So if I solve this for the mass, I get mass is equal to density times volume. And so I could just plug that in for that mass sitting there. And I see that the weight is the same as the density times the volume times gravity. Okay, so just a little trick, a little math trick where you have two different equations, but they're related in some way. They both have mass in it, let's say. Then you manipulate one of the equations and you stick it into the other. And now you've replaced the mass with something else you know, which is in this case density. And so we could use that fact now and say the weight of the fluid that was displaced, well, that's the density of the fluid times the volume of the fluid times gravity. That must be equal to the buoyant force, which acts on the object, right? We know the weight of the water displaced is equal to the buoyant force, and all we did was come up with an equation to calculate the weight of the water displaced. But then sometimes it's useful to kind of combine this relationship with the second relationship, because we know something about the object, let's say. I have an ice cube. I know how big the ice cube is. So another way it's written sometimes is the density of the fluid times the volume of the object times G. is a buoyant force. These two things are the same thing because we're using that second relationship there. Volume of the fluid is replaced with volume of the object. That's all it is. And so you see both of these equations, generally speaking, because it depends on the question. The fact that sometimes you know something about the object, so you use the volume of the object. Sometimes the object is weird shaped, like I talked about the king's crown. Well, I don't know how to calculate the object of the volume of the king's crown because it's weird. So instead, I would use the volume of the water that was displaced. That's something I can get. But they mean the same thing. At the end of the day, it's just a statement that the weight of the water displaced is the same as the buoyant force which acts on the object. Okay, and this is Archimedes' principle. It's really these three here is what generally is called Archimedes' principle. But that last one is kind of a replacement for the second to last one, just depends if it's the volume of the object or the fluid. And the first one is just something handy to know, the apparent weight stuff. But the stuff in the red brackets there, that's usually what's called Archimedes' principle. And so that's what we learned last time. This was the theory. These are the relationships we have. And now, of course, I'd like to see what kind of problems can we solve using these relationships. So before I do, are there any questions about this? About what any of the relationships mean or something like that?
I got a question. So what you have in green, where it says weight equals mass times gravity, right below that, is that also another way of saying weight equals the density times volume times gravity?
That's right, right. There's an equal sign here. And all I did was replace this mass with this mass here. Right, mass is the same as density times volume by the density equation. And so I just replaced mass with density times volume, and G comes along for the ride because it's weight. Yeah, that's right.
So that's another way of saying weight equals density times volume times gravity.
Right, right. And that's how I get this relationship down here. I had weight at this part, and I replaced weight because I now did this stuff with density times volume times gravity. Yeah, because that's usually what you know in a problem. You won't, the problem won't say, hey, you stuck a king's crown in the water and 20 pounds of water was displaced. You know, you never know that. But what you do know is, well, it's water, so I know the density of water. I know maybe the volume, a certain amount of water came out. How much? Well, 2 liters of water or a gallon of water or something. So you know the volume of the water. And of course, G is 9.8. So generally, when you have a problem or you're working on an experiment, those are the things you actually know. You don't know what the weight is, but you need to know the weight to solve for buoyant force. So that's a calculation to get the weight, basically. Any other questions? All right, so let's take a look at an example. Let's try an example. So here's a pretty easy example. It seems like a complicated question, but there's a nice, easy relationship here that's will make our lives a lot easier. A boat, let's say, made of wood and steel is, let's say, 50 meters long. When placed in water, 1/4 of the boat becomes submerged. what must be the density of the boat? All right, so here's what could be if we were an actual engineer or something like that, and we were asked by a company to try to figure out the density of a boat. That would be a very difficult thing to do. Because of course, if we want density, it's the mass of the object divided by its volume. And a boat is usually made of a whole bunch of different materials. So we can't just say, well, the boat is made of wood, so we just take the density of wood. There we go. No, because it's not a solid piece of wood, it's hollow. And like I said, there's, maybe a computer in there, there's the electronics, all sorts of stuff, the different chairs, different fabrics. And the shape of the boat is probably not straightforward. It's not like a cube or a box or a sphere. It's probably some interesting shape. And so trying to figure out the mass and the volume would be fairly difficult. Thankfully, though, there is a relationship. We know, for instance, the fact that an object will float or sink based on its density. Remember, the greater the density relative to the fluid, the more likely it is to sink. If you have an object whose density is greater than a fluid's density, the object will sink for sure. And if the density is less than the density of the fluid, then it'll float. And so we can use that fact and we say, okay, well, look, if a quarter of the boat is submerged, then that must tell us something about the density of the object. If all of it was submerged, if 100% is submerged, then we know the density of the object is at least the same, if not greater than the fluid. So the first thing I know is the boat's density has to be less than the density of the water, because most of it is floating, only some of it is submerged. But the exact relationship goes like this. The percent submerged, or the fraction submerged is another way of saying that, is given by the ratio, or dividing, the density of the object you're talking about divided by the density of the fluid. And we could ask ourselves, is this true? Because it's very easy, even for me, because I don't use this very often, to remember the order. Is it the density of the object divided by the density of the fluid, or vice versa? Is it the density of the fluid over the density of the object? Well, one way of thinking about it is, if it's 100% submerged, so all of it's under the water, it's sinking. So I would expect the density of the object to be bigger. And so if this number on top is bigger than this number on the bottom, then I get a number bigger than 1, bigger than 100%. Perfect. If none of it is submerged, if it's completely floating, then I would expect the percent submerged to go to 0. And that would be a number less than 1, which means the numerator would have to be less than the denominator. And so that, in my brain, is what helps me remember, if I don't have the equation in front of me, is it the object on top or the fluid on top? Well, here, the object's on top. So that's what I want to calculate. I want to know, what is the density of my boat? So I solve this for density of the object is the density of the fluid times the percent submerged. And now on a test, of course, you'd be given the density. Any density you need that you're not going to be calculating will be given to you. And so we just remember the density of water is 1,000. So the boat's placed in water, density of the water is 1,000 times the percent submerged. I'm told 1/4 of the boat is submerged. So that's 0.25. 1/4 is 25%. Or you could just literally put 1/4 as the fraction. The percent submerged is the same as the fraction. And so we plug this in the calculator, of course, and we get, what is it, 250 kilograms per meter cubed. And then, of course, we could ask, does it make sense? Again, the boat is floating. Most of the boat is above the water, so it's floating. So the density of my object better be less than the density of the fluid. Well, the density of the fluid is 1,000. My answer is 250. So it works. It makes sense.
Oh, what are the units that's next to 250?
Yeah. So the units of density are always kilograms. So mass divided by volume, right? Mass is kilograms, volume is meters cubed. Okay, so just remember the equation. Density is mass over volume. Units of mass is kilograms, and the units of volumes is cubic meters. So any questions? Yes.
Yeah. I'm confused on how to know which formula you use, because you did the percent submerged formula, but we didn't write that one earlier.
Yeah, that's fine. I know. And that's kind of the issue with this particular section, is there are a lot of little bitty equations. So if I want to make sure I include all of the equations, not just what's necessarily called Archimedes principle, then there's two more we have to remember. The first is the one I just did. Percent submerged is density of the object over density of the fluid. Now, the reason this I don't include in Archimedes Principle's set of relationships is because this is only used in one spot. It's only ever used for this question. You know, the question where an object is placed in the water, how much of the object will be submerged, or how much of it will be above the surface, or 2/3 of the object is submerged, so what must be its density? All the questions that relate the fraction that's submerged or how much is above the water to the density, that's when you use this equation. But that's the only time you use this equation. These Archimedes ones over here, there's a whole set of different types of questions that can be asked where they may be useful. So this is kind of like a one-trick pony. It's an equation that's useful for what it's useful for. You know, this question is a difficult question. It's very complicated if we actually wanted to do it the right way, which is to actually calculate the mass and try to calculate the volume. That would give us the density. Of course, we don't want to do that. That's way too hard. So instead, here's a little trick that happens to work. The problem is the trick only really is useful for this type of problem. The other equation, which I mentioned, is the pressure depth relationship one. And it says the pressure that you would feel, depending on how deep you go, is given by density of the fluid times gravity times the depth, how far down you go. Okay, and again, this is not Archimedes principle. This is just an equation about the relationship between pressure and how deep you are. And remember, we also used it when we talked about Bernoulli too. It was up in Bernoulli's equation. It was just not in this type of form. So really, you know, if we're putting Bernoulli aside, so Bernoulli and continuity, we did that, and now we're on this other topic, then these are the equations, all the different equations we need for this particular topic. The ones on the left, those are what's referred to as Archimedes principle. And the ones on the right are just some extra ones that pop up for certain questions. The good news is the ones on the right, which pop up for certain questions, when you see the question, you know which equation to use. The Archimedes one, that's a little bit more creativity involved because it depends on the relationships. But like when you see this example, you know, bam, I have to use a percent submerged equation. That's the one I use. And that's the only one I can use. Or A question like a diver goes down 150 meters in the ocean, what kind of pressure would he expect to feel? Well, that's pressure depth relationship, of course. You're talking about what's the pressure depending on your depth. So those are kind of straightforward. You see the question, this is the equation I use. So in the Archimedes one, do I use the displaced volume, the volume displaced equals volume of the object, or do I use one of these other ones? It's not as straightforward, but they're all kind of lumped together.
Dr. Rosman,
Sure.
I don't know if we finished the last example from the last class. The second part, when you said the example would be, I mean, we could really apply it to the one you just did now, but the question was calculate the fraction of an iceberg submerged.
Oh yeah. Good. Yeah, I forgot about that. Right. So let's see. Let me look up really quick just so I have the numbers, and then you can compare. Hopefully everybody did it. You'll be able to compare your numbers. So yeah, the question was, there's an iceberg sitting there, and you're looking at that big old iceberg in the water, and you want to know this kind of rumor, or the tale that they say is that even though when you're looking at an iceberg, it's a big old iceberg, that's actually only the tip, and most of the iceberg is actually under the water. And what we like to do is confirm if this is true. And to do it, we need to use this equation, the percent submerged. We're going to find out how much of my iceberg is under the water. What do I need? I need to know the density of ice, and then I need to know the density of the water. So for that one, I'd say percent submerged is the density of the iceberg over the density of the water. And I said that, remember, the water is going to be salt water, not fresh water. So I look up in Google density of ice. What do we get? I don't want those units. In kilograms, there we go. So density of ice, I get 917 kilograms per cubic meters. And then I need the density of salt water. Salt water. And for that, I get 1026. By the way, notice the density of salt water is not the same as the density of fresh water. Fresh water is 1,000, salt water is a little bigger. And so one thing this means is that since the density of salt water is a bigger number, then more things can float in salt water than in fresh water. Because remember, in order to sink, you have to have a bigger density than the fluid. Well, if the fluid has a bigger density now, then you're more likely to float. And in fact, it's true. If you go into salt water, you're going to float a lot easier than if you're in fresh water. And when you're in super salty water, like the Dead Sea, then you float really, really, really well. Anyway, that's an aside. So 917 divided by 1026. Oh, shoot. Let me do it on my other. The calculator I happen to bring with me only gives me fractions. 917 over 1026. I get 0.8937, which means 89.4% of the iceberg is actually submerged. So when you look at an iceberg, mathematically, we've just proven when you look at an iceberg, all you're looking at is 10% of the whole iceberg. 90% of that iceberg is actually under the water. And so indeed, it's true what they say. And that's why they say it's only the tip of the iceberg, because this big old iceberg you see in the water here is actually way bigger, and you're only looking at the top 10%. Everything else is submerged underneath the water. And so I hope everybody saw the same thing. Of course, the numbers, depending on where you get the densities from on Google or in different like tables, the numbers might be slightly different. But at the end of the day, you should get an answer similar to this. Something like 90% would be submerged. Are there any questions about that particular problem or example?
Could you repeat when you said if the submerged percent was 1?
Yeah, so if you get, so let's say the density of the ice was 1026 and the density of the water was 1026. Well, when I do that, I would have 1. The answer would be 1. And what that means is 100% of the object is submerged. Now, of course, that would mean we have, here's our water, and our object is just sitting down underneath the water. Now, it doesn't mean it's sinking, like actually falling down to the ground. And it doesn't, of course, it's not floating either. If you get this object that happens to be exactly the same density, and you just stick it underneath the water somewhere and let go, it'll just sit there. If its density is a little bit more, then it'll actually fall. It'll literally sink to the bottom. And if it's a little bit less, it'll float back to the top. So a density of 1 is kind of that extreme case where the densities are the same. They're exactly the same density. And so you're on the edge of sinking versus floating. But we would still consider it sinking. You know, floating is when some of you is above the water. That's kind of how we define floating. Okay, so does that answer your question?
Yes, it does. I also have a second question. If it's like that, then would you factor in force of buoyancy?
Well, that's what the reason the object would be staying like this. The reason the object is either sinking or floating is the buoyant force. So if we have that case of 100% submerged, we're exactly at 1, then what it really means is the buoyant force trying to lift up on our object is exactly equal to the weight of the object trying to fall. They balance each other out. Okay, so, and the same is true over here with the iceberg. You have the weight trying to pull it down, and you have some buoyant force trying to lift it up. But in that case, the buoyant force is a little bit less. And so it had to take some of the iceberg to be underwater so that it's now lighter, so that now the buoyant force can handle the weight of the object. Remember, when the object's outside of the water, it's heavier. So the more of the object you get into the water, the lighter it is, and thus the easier it is for the object to float. So 10% of the object being above the water and 90% being below the water, well, that 90% feels lighter now because it's underwater. And so the buoyant force can now balance. But an object which is at 100% submerged, let's say, well, that's a perfect balance. The object's under the water, gravity is trying to pull him down, buoyant force is trying to push him up, and they balance each other perfectly. And that's why he just sits there. He doesn't go up and he doesn't go down. But all of this, everything about floating and sinking, it's all the buoyant force is the actual thing doing it. The buoyant force is that force which gives rise to the possibility for something to float. Otherwise, there's no buoyant force, then everything would sink every time. Everything would just sink to the bottom, no matter what its density is, it wouldn't matter. But because there's a buoyant force, that's what allows certain things to float and certain things to sink, because everything has a buoyant force, but depending on its density, it may be less or may be greater in value. You know, maybe a bigger buoyant force or a lighter buoyant force. Any other questions? All right, so let's see. Let's try this question here. right, you have a metal sphere. Whose diameter is 1 meter. The density of the metal is, let's say, 5,500. What would be its apparent weight when placed in water? All right. So here's a question. Now, this is more Archimedes style. I have something about apparent weight. So first thing I know for sure, I have the apparent weight equation. Apparent weight is true weight minus buoyant force. There's my equation. That's what I want to do. Now let's see if we can do it. Okay. First thing I need to know is my true weight. Do I know the weight of my sphere? No, I'm not told the weight. I know nothing about the mass. All I know is the size of the sphere and its density. So I first have to work on true weight. Let's do that first. I know weight is mass times gravity. Okay, but I don't know mass. However, I do know the density, right? And I know density is mass over volume. So I could use that equation to solve for mass in terms of the density. Mass is density times volume. So now I know if I want to calculate the weight, which I need the mass, which I now know is density times volume, times gravity. Okay. Now I can ask myself, do I know these things? Because if I know these things, then I'll plug them in my calculator and I'll get an answer. So density, do I know the density of my metal sphere? Yes, 5,500. Perfect. 5,500. Next, do I know the volume of my metal sphere? Not exactly. I'm not told the volume, but I am given something that'll let me get to it. And that is, I know the diameter of this sphere. So another thing I need to calculate now is the volume. Well, volume for a sphere, if we remember, is 4/3 pi r cubed. That's the volume for a sphere. All right, so in order to calculate the volume, I need to know the radius, right? That's the r. Well, I know the diameter, so we have to be very careful that it's given diameter, but I don't want diameter, I want radius. So we say the radius is half of the diameter, so it's 50 centimeters, which is 0.5 meters, right? We're given the diameter of my sphere, but what I would need is the radius. So I divide the diameter by 2, and so the radius is 0.5. Now I know the radius. I can plug that into my volume equation, 4/3 times pi times 0.5 cubed, and that'll give me my volume. So 4/3 times pi times 0.5 cubed, and I get a volume of 0.5236. All right, so there's a volume. Fine, I now know the volume. I can continue my weight equation. Weight was rho, 5,500, times volume, 0.5236, times G, which is 9.8.
How did you get 0.5236? I got 0.523 repeating.
When you did pi, did you plug in the simple pi or 3.14?
I did 3.14.
Yeah, I think that's the difference. On my calculator, I just plugged in the simple pi and I didn't do any rounding until the answer is rounded a little bit, because my answer is 0.52359999999. So I rounded it up. So I think that's the difference. I don't think that's going to make a big difference in the final answer, though. So let's go ahead and calculate what use your number, calculate this out, and we'll see if it's the same number, relatively speaking. Because if you're only off in the 4th decimal, well, that's pretty good. That's not a big difference. So what I get when I multiply these things, 5,500 times 0.5236 times 9.8, I get 28222 as my weight, which would be in newtons if you want the units. Okay.
I got 28,205.
Yeah, I think that would be close enough. If this were a test, let's say, then I would see, okay, the reason is 3.14. I wouldn't take off for that. But if you want to know the reason why my number is slightly off, my calculator is doing 3.141592653. It's using all the numbers, whereas you're using 3.14. It kind of rounds it a little bit, and so it's just off a little bit.
Okay.
Yeah, so that's okay. So I now have the true weight. Before I go on, are there any questions about what I've done so far? So we want the apparent weight. So there's the apparent weight equation. Apparent weight is true weight minus buoyant force. First thing I need is the true weight. Do I know it? No. So I have to calculate it. Weight is m times g. Do I know that? No, I don't know m. So now I say, okay, well, how can I get mass? If I know density, then I could do density times volume to get mass. So I replace it. Now I say I need density, I need volume, I need G. Density is given in a problem. Volume is not, so I need to calculate volume. So I'd calculate the volume. I'd be careful. Remember, I need radius, not diameter, so don't let it trick you. Calculate out my volume, plug it in, and now I have the true weight of my metal sphere. All right, but that's not the answer. This is just the first piece of my answer, the true weight. That's now done. Next, I need the buoyant force. So I need to figure out a way to calculate the buoyant force. Well, if you go back to Archimedes Principle stuff, we see here, right there, there's an equation for buoyant force. Of course, this one is too at the bottom, right? Buoyant force is rho times V times G, whether it's for the fluid or it's for the object. So that's what I'm going to do. My next calculation is calculate buoyant force. And I know buoyant force is rho of the fluid times V of the fluid times G. Now I ask myself, do I know these things? Do I know rho for the fluid? Well, it's not given in a problem, but on a test it would be given. This is water, and I'm just assuming we know density of water is 1,000. So yes, I know density of the fluid, it's 1,000. Do I know the volume of the fluid that's displaced when I place this sphere in? Well, no, I'm not told anything about it, but Archimedes' principle told me that the volume of the fluid displaced is the same as the volume of the object, which is how I get this equation down here. So I know the volume of the object. That's perfect. This equation is actually density of the fluid, volume of the object, times G. And now I could get this. Density of the fluid, that's 1,000. Density of the object, well, I calculated that before. It's 0.5236 times 9.8 for G. So 1,000 times 0.5236 times 9.8, and I get 5131.28. Okay. And so there we've calculated the buoyant force. We use the little trick of the volume of the fluid displaced is the same as the volume of the object, because I know about the object, so that's the one I use. The density of the fluid, that's easy. This is water, so it's 1,000. If this were another problem where it, you place this in honey, then obviously the density of honey would be something else. You'd have to get the data for that. But anyway, we calculated out. We now know the buoyant force. That's how much the water is trying to lift up on the sphere when we place it in the fluid. Now I have the true weight. Now I have the buoyant force. I can now finally solve my problem. The apparent weight, how heavy the sphere would feel in the water, is its actual weight, 28222, minus the buoyant force, 5131.28. So 28222 minus 5131.28, and I get 23090.7 newtons. Does it make sense? Well, I placed the object in water. It should feel lighter. Its original weight was 28,000. It's now only 23,000. It feels lighter. So yes, that works. And so that is a nice classic Archimedes principle style of problem. You could see it's a lot different from our previous example. Previous example is straightforward. We want to know the density of the object based on how it's submerged. There's the equation, plug it in, get your answer. This example and all of Archimedes' examples are kind of like this. You're asked for something, so you have an equation, there it is. But likely you don't have all the parts of that equation yet. And so you're going to do a series of little mini calculations to gather up all the information to plug into that main equation. Here, I need to know the true weight of my object, and I need the buoyant force. So I work on them. I do a little calculation on the side. Here's how I calculate the true weight, plug everything in, get my number. Then buoyant force, another calculation on the side. Plug in everything to calculate the buoyant force. I now have him. Now that I have that stuff, I could go back to the actual equation and plug the numbers in to get my answer. And so that's what I mean by Archimedes' principle being kind of this series of relationships that are interconnected. They're all related to each other, and they all help you get some piece of information you may need to do something. What to look out for, generally speaking, you want to be sure you're using the right units. So kilograms for mass, meters for volume, stuff like that. You want to make sure that you're not doing centimeters. For instance, if I said the diameter is 50 centimeters, you got to convert that to meters. Also, look out for diameter versus radius, because that pops up a lot. They give you the diameter of an object, but of course the calculation actually wants you to use the radius. So you have to be careful about those little bitty things. But other than that, as long as you know what the relationships are, and of course you'll have the equations on the formula sheet, then it's just a matter of which equation do I want to use to get my answer? What are the pieces of information I need to use to get that answer? And then go get those pieces of information using these relationships. So any questions about this?
Will there be any homework problems for Archimedes?
Yeah. So what I'm going to do is this. Tonight, I'm going to post a homework assignment for Archimedes Principle. And then I'll go ahead and postpone the test to Monday. I'll give us one more day of examples to work on. So Wednesday, instead of the exam review, we'll do some more examples just to make sure we know it. And then Friday will be the test review. Okay, I think that should be, I don't think that's going to delay us too much because we'll still have optics to do before the final exams and we'll still have time to do all that. So I'll go ahead and postpone a test by a day, our class period. Wednesday, we'll do examples, Friday, the test review, and look tonight. Of course, I'll email you when it's posted, but yeah, I'll post a Archimedes style homework assignment for you to work on as well to get some more practice in. Other than that, are there any questions?
Just to reiterate and get clarification, the test is on Monday, you said?
Yeah, the test now, I'm changing what I said a little earlier, will be this coming Monday. Again, it'll be online like the last one. So Monday morning, the test will be posted. You have the full day to work on it, download it, fill it out, and then submit it back on Canvas. So that'll be this coming Monday. Friday will be the test review to prepare us for it, or last minute questions, stuff like that. And so this coming Wednesday, we'll do some more examples like this to get some more practice in. That's right.
Thank you so much. I appreciate it.
You're welcome. Well, if no one has any more questions, y'all are free to go, of course. Look out for the homework assignment to be posted. I'll send an email about it. But other than that, I will see you on Wednesday.